We work at Facebook on the Data Freeway team, and we'll talk to you about the real-time elements of our system today. So there's a few things, actually, I hope that will come out today. I hope to give you a rough overview of what the data looks like at Facebook, how the Data Freeway fits into shoveling that data around, and a little bit into our real-time components, with some emphasis on Calligraphus, HDFS, and Puma. All right, so I think the takeaway from the top half of the slide is that a lot of people spend a lot of time doing a lot of different things on Facebook every day, and this generates a lot of data. In fact, most of the data numbers on here are probably 6 months or more out of date, but they're the only official ones I have. The only one I can actually update here, changed shortly after I generated the slides, is the 4 gigabytes a second is actually 7 gigabytes a second. So it's quite a bit of data. On the product side, we do both batch and real-time applications, but we'll again focus on things related to real-time today. So this is a 30,000-foot view sort of the Data Freeway. We'll start on the left-hand side here. This basically represents every machine at Facebook running a Scribe daemon. Scribe is the entry point into the Data Freeway, and whether it's a web server, some other sort of back-end service, a user script, a cron job, or what have you, they just send data to their local Scribe daemon and it enters. As far as getting data out of the Data Freeway for real-time use cases, we have this client-side application called ptail, and then people can write their customized apps on that, getting a stream of data out. We also have Puma, which is our emerging real-time analytics system built on top of ptail. So as far as requirements on this real-time system, some additional things to add to this here. The scalability also needs to be a real-time scalability, operational scalability, meaning when we add machines and so forth, we don't want to do a lot of manual rebalancing or what have you for hotspots, for read or write and what have you. Some additional clarification too on the different SLAs. They're both in the light, SLAs being the data loss, and the latency. They're both with respect to hardware failures. There is no data loss in the system if there's no hardware failures, but in the light of a certain failure rate, we want to try to minimize and cap the amount of failures that we see. And this is similar for the latency side, which is why we offer this 99th percentile 10-second latency. Typically, it's going to be more like 2 seconds. And lastly, of course, it has to be very easy to use. We had previous use cases that looked about like this when we used to use NFS. So a couple major points, or sorry, two major elements that I think are important that Scribe offers the Data Freeway. First is that it's reliable. What this means is that if the end user submits a message to the Scribe system and the downstream system is not up, Scribe will actually buffer the message locally until the downstream system is available. Second, it's very easy to use. It's got a Thrift API, so we have a diversity of languages being used inside Facebook. People can send messages using PHP, Python, Ruby, Perl, compiled C or C++ binaries, Java, or what have you. And I like to emphasize that I think this element of Scribe and the Data Freeway is why we're doing 7 gigabytes a second, because it's just very easy to get data that's useful also to get out. So the next piece is Calligraphus. In a nutshell, it's basically a distributed logging service, much like Scribe, but written in Java, and it's compatible with Scribe. And I think with regards to why, there's really 2 dimensions to that question. The first might be why rewrite Scribe or something similar, and second, why Java? To the first question, we were basically looking at adding some stream consolidation that Eric will talk about a little later to Scribe. And we just thought there was going to be too much risk. Scribe had accumulated a lot of different special cases for different teams within Facebook, and the work that we wanted to do was just going to be kind of gutting it out. So we decided it was easier to extract the simple parts that we used, the smaller subset, and build something new. And once we decided to go with something new, we figured that it was best to go with Java because we'd had some issues with JNI, memory leaks, and translating exceptions to error codes. And also the rest of the Hadoop ecosystem was in Java, and we thought we could leverage components there. Oh, and I noticed an error on the slide. That should say November 2010, in case anyone's wondering. Yeah, it's a long, long time. Yeah, and another note here, we actually do hope to open source Calligraphus probably in the coming months or so. Not completely sure on the timeline there. So this is hopefully to give you an idea of sort of how HDFS fits as this message hub in our real-time system, which is really kind of really boils down to almost like a pub subsystem. If you look at the left-hand side and think about these, say, as web servers, all they're doing is logging a message to Scribe, and they're just tagging the message with a category, say category 1. They're not worried about anything downstream. Calligraphus and the data Freeway figures out what HDFS cluster to write it to, what the file path is, and so forth. And then HDFS takes care of the replication and the reliability element there. On the other side, to get the data back out, they use our PTEL client, and they, again, just say, I want data for category 1. They're now a subscriber. And PTEL figures out what cluster to go to, what the paths are on that cluster, and HDFS then sorts out the replicas to read from and so forth. And then this way, like I said, you have a pub subsystem on top of HDFS, and you get all that HDFS gives you for free. So in order to get to that, though, we started with stock Hadoop 020, I should rather say, and there are a couple of things we have to add first. The first was sync support. We needed a way for writers to be able to guarantee that their data had been persisted to HDFS. And at a high level, the way we went about implementing this is when a client makes a sync call, it first contacts the name node and asks it to persist the current blocks being written, the locations, to its transaction log. It then flushes the data out of its buffer through the write pipeline. And so the invariant is that after sync has been called, the blocks have been persisted in case the name node goes down and comes back up, and the data has been written to every data node's disk. As an edge case, it may be in the OS buffers, but the probability of data loss there is pretty low. Oh, and one other thing I should add, we don't do sync very often. We do it about every 7 to 10 seconds, because some in experiments on the H-based write-ahead log, we found it cut the throughput to about half when you're doing very, very frequent syncs. So sync is only half of the problem here. Recall our 10-second latency goal. In order to make that without making any changes, this would mean that the block being written couldn't be read and that we would have to wait for it to be finalized or the file to be closed. And we close files once an hour, so at the very least, that we got to do better than that. And we use block sizes of about 512 megs, actually. And even if you go lower, down to 64 or 32, and even with the 7 gigabytes a second, spread across thousands of files, we're just not going to be filling up a block every 10 seconds to make it available for read. So it becomes obvious that we need to actually have this concurrent reader support to make our latency requirements. So again, at a sort of an overview of how we went about implementing this, when a client, wants to read a file, it goes to the name node, and we modified the FS name system inside the name node to return the locations of the current block being written as a located block. Then the client looks at this, and if it wants to actually read that last block, the length is actually stored on the data nodes that are receiving the data, and it will contact the data node, get the length, and it can then build the right data structures to start reading. There's one potential pitfall or caveat here. Because it's a write pipeline and there's actually going to be more than one data node receiving data, in the 020 implementation, it's actually possible to read data from one data node, have that data node die, and subsequent reads will not see that data anymore. So you can actually read data that disappears. The trunk at the time we did this, which is 22 now, actually doesn't have this problem because it has a better visible length model. So one other problem that we dealt with was the checksum problem. And what this boils down to is that the data and metadata being written on each data node for a block can actually be out of sync. The metadata here is a checksum, and it results in checksum errors if you happen to catch it at the second or fourth case on the screen here. And so in 020, what we actually did is just detect this. So when you create the appropriate block sender object in the data node, you track the length of the data at that point. And if anything is added, you actually just do this dynamic recomputation of the checksum. In trunk or 22 again, it's a little bit more elegant in that this last little partial chunk depicted here, we actually keep the checksum for that in memory. And so we can atomically, when we create these data structures, get a length of data that's available and this checksum for the last partial chunk, and avoid the problem. There.
So Sam just went into how we did some of the real-time aspects for, So Sam just went into some of the aspects of how we did real-time reads from HDFS. And I'll be going a little bit into the design of how we improved operationally the real-time aspects of one of our components. And specifically, the component that I'm going to be going into is called Calligraphus, which Sam mentioned earlier. The primary role of Calligraphus in our system is to take incoming log streams and persist them to HDFS. A very simple role, really. Just to kind of give you guys a little bit of context of what this setup looks like. We have thousands of client servers. These can be like web machines or individual team-owned servers that are submitting data through Scribe to Calligraphus. And each of these servers are generating a very large number of categories. And since, as a form of load balancing, we randomly distribute these messages among our Calligraphus servers, the Calligraphus servers themselves are operating, or they can be operated under the assumption that the load among them will be roughly uniform, and that every category will be distributed to roughly every server. And that's kind of depicted in this sort of this cross product going on. And so the real question that we have to ask is, how did we design the system to persist this to HDFS? In reality, there are 3 constraints that we have to respect when we design the system. The first is that every Calligraphus writer, the output stream that going to HDFS has to appear as one directory in HDFS. And this is because as data is written through that output stream, it gets appended to files. And we roll files eventually, and so downstream components eventually look at these directories, and they're able to bring out this information at what seems to be a stream, and oftentimes they pull it on a per category basis. The second requirement is that each category must be written to its own stream, and this is so that obviously we don't get sort of categories colliding with each other. And the last thing is that each Calligraphus writer must be writing, or 2 writers should not share the same stream for obvious reasons. So a very simple solution to this problem would be just to have every Calligraphus server take each of its independent category streams and just write them to HDFS as their own directories. So in general, this works, and in our experience, it does work, but the problem is it scales out. It has some problems scaling out to a larger number of categories and number of servers, and this is because the total number of directories, the total number of output streams that we generate is the product of our 2 inputs of our system, which is the number of categories and the number of servers. And so this creates issues because the name node itself has a finite number of resources in which it can store metadata about directories and files and such, but also because there are issues with the huge number of output streams getting written to HDFS. And the replication involved, there's just a huge number of threads and a huge number of TCP connections that are ongoing. And as these 2 inputs get larger and larger, it's just not scalable for us. So a much better solution, and this is the approach that we actually took, is what we call stream consolidation. In this approach, you take the single Calligraphus writer and then you break it into 2 logical components. There's a router and a writer. So the writer itself is assigned some subset of categories. And the router has some mechanism by which it can look up this mapping between writers and categories. And we introduced a shuffle phase between the router and the writer step that allows us to direct the appropriate categories to the proper writers. In this way, we can minimize, by consolidating the streams, we can minimize the total number of HDFS directors and output streams that we create in our system. And really the crux of this system lies heavily upon how we use ZooKeeper. In our use case, we use ZooKeeper as a platform for task allocation as well as a form of distributed map for the routers. And I'll be going a little bit into how we do that. So ZooKeeper is a distributed coordination system, as Sam mentioned. It can also be viewed as a sort of distributed file system of sorts, where you can put and get information in the form of paths. The paths that we define are category bucket pairs. In this case, it would be something like root category bucket. And we introduced the concept of a bucket in addition to a category in order to subdivide category streams that may be too large to be handled by any given writer. And so this allows us to break it down into manageable units. Under each of these paths, we run the canonical ZooKeeper leader elections. And I'm not going to go into how that's done because you can look that up on the web pretty easily. But through the leader election process, we're able to determine the owners of a particular category bucket and to determine which writer will be actually handling that unit of work. This process is roughly random. Bootstrap hosts randomly join elections, and so the result is that any given Calligraphus server will be serving a load in somewhat of a uniform, of a normal distribution among all of our Calligraphus servers. And so there's going to be that high end of Calligraphus servers that won't actually be able to handle all of their load. And so we have an independent load management process where each Calligraphus server inspects their own load and determines whether or not, or what subset of the tasks that it's been assigned and which subset of it that it actually wants to keep. And it does this without consulting any other nodes. In order to increase our QPS to ZooKeeper, even though ZooKeeper has a very high read throughput, it's still a network I/O, and so in order to increase that QPS rate, we have very aggressive reader-side caches. And we do this by basically replicating every important aspect of this hierarchy into each Calligraphus server's memory. And so this works for us because the mapping itself, once it's been stabilized over time, rarely changes. And so we can get this very high QPS out of that. And the last point that I would like to make is how we kind of evolve or adapt our system to changing environments. And what I mean by this is obviously we have a growing set of categories in our system, and so we have to continually add new elections for these categories. And so what we have is we have a registration database somewhere where users can register their categories, and then we have a synchronization process that pushes this information from this database into ZooKeeper. And so as categories get registered, we can create new categories, and as their throughputs change, we can change the number of buckets allocated under each one. And in this way, we can kind of dynamically control the number of elections and the number of units of work that we've been allocating out in our system. And so using ZooKeeper really affords us some very nice properties. The first of which is the most obvious, in that ZooKeeper, being highly available, provides our system with its same highly available kind of semantics. We can lose a couple of ZooKeeper nodes and the whole service keeps on ticking without any interruption of service. One of the main design principles that we had with Calligraphus and ZooKeeper was to kind of avoid having any single points of failure. Everything happens perfectly distributedly. There's no real collaboration between each of the Calligraphus servers or among the elections. The elections are completely independent, and the Calligraphus servers independently compute load and shed load and accept load and so on. And as I mentioned before, through our reader-side caches, we can get very high read QPS, looking up mappings between the routers and the messages that are being delivered. And one nice property of the canonical ZooKeeper leader election is that it gives you inherent failover. And so what this means is that if the leader dies, or if any of the candidates die, the successor immediately gets notified of this change, and it can take over right away without any or very little interruption, actually. And as a result of our synchronization process with our registration database, we can adapt our system very quickly to changing environments at Facebook. So all of this is very high level and very abstract. So just to kind of bring it down to earth and give you guys some examples. In our system, we have something like 3,000 categories at Facebook. And if we take a look at the bootstrapping phase, which is really the interesting part of this whole thing because it kind of stabilizes after a while. For the writers, it takes something like 30 seconds for all of the writers to participate in more or less all of the elections. And for the routers, it takes them, once they start scanning, it takes them something like 5 to 10 seconds to get the full mapping. And it's important to keep in mind that at this point, the mapping itself has not actually stabilized because the elections are still going on and people are still figuring out load of whether they can handle this set of tasks or not yet. So in reality, it takes something like about 3 minutes for all of this election process to go on before we come out with some stable mapping of categories to writers. And the last thing I'd like to point out is that by using ZooKeeper watches, we're actually able to respond very quickly to changes in ZooKeeper. Usually this is less than 1 second, and we can respond within less than 1 second to things such as leader failures and as well as changes in the map or like new categories that get added and so on. And the worst case is bounded by ZooKeeper, and that's in the tens of seconds.
Okay, I just wanted to bring this back real quick to the overview of what we're trying to get to, just real high level. We want this app that's on the left-hand side that writes data without knowing much about what's in the middle. It could be an NFS file or what have you. And the right-hand side just basically tails a file. So we're not quite there yet. We need one more piece, which is ptail. 2 pieces about ptail. Sorry, 5 or 10? He says 10. Okay, I'm going to need about 7. So anyway, I've got a stream here. Basically, once you have ptail, you can get a stream by a category name. And you specify that, and all this, the inner workings before that Eric talked about are all hidden from you. The second thing that's important about ptail, aside from this simple stream, is reliability. It periodically emits a checkpoint string, which if you persist to, say, a database, you can start ptail back up with that and get data back from that point. You get a small amount of duplicate data, that which you might have read after the last checkpoint, but you can solve that in the app side. So now this is what the app looks like. You've got scribe on the left-hand side. People write to that local scribe daemon, figures out where to send it, which Calligraphus instance, what the file paths are, ptail, then figures out what clusters to read from, what the paths are, and so forth, and the app on the other side just gets a stream. And real quickly, I'll shorten this as much as I can, but Puma is our emerging real-time analytics platform, and it's actually that canonical real-time app. It's sort of we're eating our own dog food in Data Freeway. And basically, it's config-driven and possibly moving towards streaming SQL. Other note here is it also uses HBase for persistence. Let me go into a little bit about what it looks like. So you've got ptail emitting log lines here. The driver component inside a Puma node passes these the raw line off to a pool of worker threads that parse the lines and also process them and send them off into the appropriate memory store for in-memory aggregation. Then when ptail emits a checkpoint periodically, it gets passed off to a checkpoint handler, which decides if it's time to flush or not. If so, it triggers a flush of the in-memory data from the aggregation store, and then the checkpoint handler will also persist the checkpoint after that's done. And as I noted, currently we have a storage layer that's abstracted out, but we write to HBase. On the read side, things are actually quite simple, and just something that Yorm was alluding to earlier. This isn't the same server right now, but for isolation purposes, we'll want to separate this out. There's no interdependency between these components right now. But basically, it's just a thrift server that's proxying requests to the storage interface, which then in turn proxies to HBase or what have you. And that pretty much wraps it up. Aside from what the slide shows here, if you want to remember some pieces, Scribe and Calligraphus are a distributed logging service, which get the data into the system. HDFS is at the core, providing reliability, replication, and so forth. ptail is the tool to get the data out in a very simple way and with some reliability elements built in. And Puma is our emerging real-time analytics platform. And the last little slide I'll just put up. If we're really out of time, I can skip this. Oh, well, I went too fast. So these are some pieces we're adding. Puma is the thing we're adding the most features and functionality to. Here, basically, when I talked about ptail giving you the same data a couple times, for Puma, we're going to need this application-level transactions so that we can actually have precise sums and counts and not overcount a little. We're also working on having a streaming SQL interface so that we can compile SQL down to our config file format right now. And this will make it a lot easier for people that run Hive queries and jobs around Hive queries to transfer over to Puma. And the last little piece we're working on, we're deploying soon, is it's basically just a container format that gives us 2 things. One is the ability to seek to an uncompressed offset in a compressed file without decompressing the whole thing. And the second is it makes any compressor flushable. And that's basically because it has these sort of virtual files inside of it. So that's it. Thanks. Oh, can you go up to the mics?
You should use the other mic.
Did you consider using HBase instead of building your own the logging system? So using HBase instead of writing to HDFS and all that kind of stuff?
Yeah, we actually did. And I didn't do these tests, but one of my coworkers actually ran some tests, and the write rate that we need, we couldn't make it. It just, unfortunately, weren't able to, even with different configuration operations in HBase.
Do you know by what factor it was slower? Or?
I don't have those numbers off the top of my head, but okay. I can tell you right now we have a different architecture of Puma where we're sending basically counter operations to Puma, and it can't even keep up with maybe not even 10% to half, somewhere in the 25% range of our data rate. So.
Gotcha.
Hi. For data uploads, I mean, it sounded like you do sync in ACTS from the clients that are actually uploading. What happens if that machine who's uploading dies during the period, and Do you lose data actually on that machine, or it resyncs?
So let me just make sure I understood the question. You're saying that on a local machine, when the client uploads and the downstream is down and it's doing the buffering, is that what you were saying?
On the scribe, I believe you call it on scribe, yeah.
Yeah, there's no way around that, unfortunately, yet.
Okay.
So,
okay.
yeah, that's the hardware failure data loss that I'm actually
that's
talking
the 0.1, okay, thanks.
Yeah.
Do you preserve any ordering of the messages? I mean, when you do shuffle and stuff?
There's no guarantee. That's actually a bit of a problem in the real-time side. It's kind of on the order in which they're received by the Calligraphus tier. They're written out, but they can be out of line a little bit.
Do you have any, in Calligraphus, do you have any provisions for handling sort of bad actors who wind up writing a lot more than sort of they promised to? Somebody starts writing 10 gigs per second, you only give them one bucket.
Currently, the load, so you're talking about just like someone who abuses and sends like, they said 1 megabyte, they're sending 100 megabytes a second.
Yeah.
Right. Calligraphus itself will do a fair amount of shuffling around to try to handle that, but we're actually in the process of dealing with this. We call it the rate limiting problem. And it's less to do just with Calligraphus, but I should add, I didn't mention this, the limiting factor in this whole system is actually network capacity right now, like the NIC. That could change with going from 1 gigabit to 10 gigabit possibly in the future, but yeah, it's a problem we actually have to solve. It comes up, category flooding.
Right. We actually have, in our registration system, we ask users to specify how much capacity they think they're going to use, and then we actually alert them if they start to exceed that limit. And so that's how we kind of control how our users use our system.
If you, So the question is about whether or not we do basically any real-time checks for attacks and what have you. That's a different team at Facebook, and I'm not sure.
What do you mean by attacks?
Intrusion detection. It's SI.
Yeah,
it's a different team. We don't actually do that. I think they get some of their data through us, actually. They're basically the customized PTEL apps. There is some of that happening, yeah. I'm not sure if I can quote these numbers. Can we give machine numbers for scribage? We've got like 500 or so total now.
Probably 700 now.
Is it 700 total scribe boxes? Or Calligraphus boxes?
Yeah.
Okay. They're not all at capacity. The problem we have is they're partitioned in some sort of way that's proprietary. And some clusters are very low and others are very hot. So, yeah.